Good morning. My name is Bill Boswell, and I'm excited to be here with you today to talk about STEM education and educating the next generation. So today you're going to hear some great stories from NASA and Boeing about risk, about innovation, and about systems-level thinking. And at the end of this presentation, I think you'll see through these experiences and projects why we need to change the way we think and why we need to change the way that we educate. According to the World Economic Forum, there are around 10 million unfilled manufacturing jobs around the world. And this Industry 4.0 graphic can help us understand why. With every industrial revolution, we see an increase in complexity and an increase in the base skills that are required by workers. And with Industry 4.0, we see advanced manufacturing becoming even more complex with that merger of the software and the physical worlds and the combination of the virtual worlds of design and simulation and the real worlds of production. So through our Global Opportunities in PLM or Go PLM program, we provide in-kind software technology grants to schools and universities. We have industry-focused partnerships, like the one you're going to hear about in a few minutes with NASA and Boeing, and we promote STEM education. You've already heard today how complex products can lead to complex processes and complex interactions, but people play a key, critical role in that life cycle. They're really essential to managing that risk side of the equation. So we have to change the way that we think and the way that we educate about advanced manufacturing. Technology can help us manage those intersections between products and people and processes, but it's really that systems level thinking and people that are going to help us change that balance to increase innovation and reduce risk. STS-107 was the 113th flight of the Space Shuttle program and the final flight of the Space Shuttle Columbia. Its crew was made up of 6 Americans and the first Israeli in space. The mission launched from Launch Complex 39A at the Kennedy Space Center in Florida on the 16th of January 2003. And during its 16 days in orbit, it accomplished a multitude of international scientific investigations. Columbia traveled 6.6 million miles through 255 orbits. The 7-member crew died on February 1st, 2003, when the Columbia orbiter disintegrated on re-entry into the Earth's atmosphere, just 16 minutes from home. The Columbia Accident Investigation Board determined that the failure and the loss of the vehicle was due to a piece of foam that broke off during the launch that damaged the thermal protection system components on the leading edge of the shuttle's left wing. So during re-entry, the damaged wing overheated, came apart, and that led to a loss of control and eventually the loss of the vehicle. This is an image of National Weather Service data that captured the breakup of the Columbia over Texas and Louisiana. More than 2,000 debris fields were found across sparsely populated areas from East Texas to western Louisiana and across the southwestern counties of Arkansas. Ultimately, more than 84,000 pieces of Columbia were recovered. After the Columbia loss, space shuttle operations and flights were suspended for more than 2 years, and construction of the International Space Station was halted, and we relied entirely on the Russians for resupply of the station for the next 29 months till space shuttle flights resumed. This is the crew of STS-114. It was made up of 6 Americans and a Japanese astronaut. STS-114 was the first return to flight space mission following the Columbia loss. It launched from Launch Complex 39B on the Discovery orbiter on the 26th of July in 2005. And its main mission was to evaluate space flight safety techniques on the return to orbit. You can see that it also took supplies to the International Space Station, and here you see the crew on orbit in the International Space Station. Can you imagine what it must have been like to be on that first mission, the return to space after the Columbia disaster? Well, you'll hear about that in a few moments. So this is a picture of the 2 STS-114 astronauts that were making their first space flight, American Charles Camarda and Shuichi Noguchi from Japan. And it's my pleasure now to introduce to you astronaut Dr. Charlie Camarda. Charlie is really the epitome of understanding innovation in that systems level thinking. He was born in Queens, New York. He attended the Polytechnic Institute of Brooklyn, where he received his undergraduate degree in aerospace engineering in 1974, and he went to work for NASA Langley Research Center right out of school. He then went on to get his master's degree in mechanical engineering from George Washington University in 1980, and his PhD in aerospace engineering from Virginia Tech in 1990. Charlie was head of the thermal systems branch at NASA Langley when he was selected to become an astronaut in 1996. So Charlie then went on later to be director of engineering at Johnson Space Center, special advisor for innovation to the Office of Chief Engineer at NASA headquarters, and he's currently the senior advisor for engineering development at NASA Langley Research Center. He has 21 awards for technology innovations and accomplishments from NASA. He's received an R&D 100 award from Industrial Research Magazine. He has 7 patents and 1 pending. Charlie understands innovation. Charlie understands systems level thinking, and probably more than any of us, Charlie understands risk. So I'd like you to please welcome me as we talk to Charlie Camarda. I have to point out one more thing. One of Charlie's papers, sorry, have to bring this one up. One of Charlie's papers was titled, "Failure is not an option, it's a requirement." Now, if you think about that in the concept of risk and innovation and someone who's an astronaut, that's pretty bold thinking. So please welcome Dr. Charles Camarda.
Thank you, Bill, and thank you, Siemens, for allowing me to be here today to talk about a topic that's near and dear to my heart: innovation, education, and solving complex problems. What Bill said is correct. Failure is not an option, it's a requirement. And I think every researcher, every scientist understands this. You have to fail in order to be successful, and there are smart ways to fail. And so I try to teach students how to fail smart, fast, small, cheap, early, and often. A couple of other things that Bill mentioned that I think are very important is we need to rethink how we think, or change how we think and how we educate. And another important point is that people are critical in not only managing risk, but mitigating risk. One of the only things he said that was wrong, or what he left out, was that the Columbia Accident Investigation Board said there was not one but 2 causes of the accident that were of equal importance: the technical proximate cause and also the cultural and cognitive biases that made these people make really bad decisions. And that's why we need to change the way we think. I put together a program to do this with several really great people. It's called the Epic Challenge Program. And what we do is we try to use epic challenges, challenges that are almost impossible to solve, to motivate, inspire, and educate young and future engineers in how to solve problems, complex problems, innovatively. Okay, so we're going to try to do this, try to accomplish all 3 things, killing 3 birds with 1 stone. This is a stark example of why we need to think differently. This is a photo of the large piece of foam coming off the external tank, bipod foam, hitting somewhere under the wing leading edge. Now, we have to understand technically why this happened, right? But more important to me was, how could these really good engineers and scientists that are the sharpest that we have, brilliant systems thinkers, brilliant project managers, make such terrible decisions? What I look at this is a bunch of left brain directed, L-directed thinkers, okay, systems thinkers that are basically following rules, processes, and procedures and thinking that that's going to make us safe just by following those. See an anomaly happen and you don't question it. We've watched large pieces of foam come off the vehicle since the 6th shuttle flight that we know of, probably every shuttle flight, and strike the orbiter vehicle. This is a failure of imagination. Imagination is the capability to conceive things which are not here, that we don't have, to think outside the box, to ask the questions, what if? No one asked, what if that large piece of foam strikes the vehicle? Well, they did, but they thought we did not have the tools to solve that problem. And this is what happened. Those same people that said there's no way, no how that piece of foam could cause damage if it hit the wing leading edge, this is what happened. 84,000 pieces breaking up over southeast Texas, almost directly over Mission Control and the people that made the very bad decision. Okay? We can't allow this to happen. So one of the first things we had to do was we had to figure out what caused the problem. Naturally, we think it was the foam now. And so what did these same engineers do? We want to get back up and flying as quickly as possible. Okay, some people in headquarters thought we should get back up and flying in 6 weeks. Absolutely crazy. They designed a very large, what I call dumb, slow, expensive test to prove that a large piece of foam could cause serious damage. So, and they wanted to do this, and we can go ahead and roll the footage now. And they wanted to do this to prove that this is what caused the problem. Now remember, people on the ground did not think this 1.6-pound piece of foam, about the density of styrofoam, hitting the vehicle at a relative velocity of about 545 miles an hour could cause a problem. What you're going to see is a very large test setup, probably $10 million, full-scale section of a wing leading edge, and only 6 strain gauges they wanted to have on this test article to understand the physics of the problem.
5, 4, 3, 2, 1, 0.
So imagine that. These really smart systems engineers, experts in structures and mechanics of this particular structure, said there's no way, no how that foam could cause damage, right? They also didn't want to instrument this. Well, we had convinced the Columbia Accident Investigation Board otherwise, and the analytical model that these engineers, researchers at the NASA research centers and in industry and Boeing developed, accurately predicted the exact damage that you see in the lower right-hand side. Not only that, but we convinced them to use a 3D full-field strain measurement technique so that we could correlate the results with the analytical models. We then use those models to basically predict failures and risk. So these are 3 birds that I want to attack. I want to attack the motivation. How do we motivate and inspire kids to go into STEM education? And I'm doing that by picking an epic challenge, something that really captures the imagination of the kids. I want to teach them using a new pedagogy. You see my expression on the left? That's why I don't play poker. That's when I was training in Russia, okay, with a very old, stagnant, stale pedagogy, and that's the expression of our kids right now and the way we think we're educating them using old techniques. Want to change that using problem-based learning, want to infuse the curriculum with innovation. How do we teach people to use their God-given talents for innovation and creativity and hone those talents to come up with breakthrough solutions to these complex problems? In all of these 3 areas, they're failures of imagination. We have good people working in every one of these areas, fantastic educators, fantastic engineers, but it's a failure of imagination. What are we not doing differently? Why can't we imagine a different way to do this? And if it's not that we don't have these great people that realize it, they're inside of a culture that prevents them from being innovative. I guarantee you Siemens is probably a highly bureaucratic organization, much like NASA, much like Boeing, and I bet there are people out there that find it very difficult to be innovative. So we have to be clever in how we do this, right? This also speaks to what Michael and Chuck have talked about, the evolution of the worker. from agrarian, agricultural, to industrial, to the information age. And what Daniel Pink says is the next age is really the conceptual age. The people that are able to use the right side of their brain and be creative to think of things that we can just barely imagine. So we've moved from an age of working an economy built on people's backs to their left brains to an economy built on their right brains. And why is this important? Why do we need to take advantage of this? Because we have a dwindling workforce in STEM, but yet in order to be competitive, I really believe we have to be able to come up with new concepts, new ideas, those breakthrough solutions to problems. And these creatives, these people that can do that are really bringing back the arts to mix in with the science. So we have STEAM instead of STEM, but they're able to visualize a totally new solution to the problem with interconnected ideas. Okay, so my big hypothesis, I think students and people of all ages love to solve problems. The more difficult the problems, the better. The more they're drawn to them. Why are kids going and adults being addicted to gaming, escaping reality, when we have so many great epic challenges in every industry for them to work on? That's our problem. Culture and environment drive creativity and innovation. Not only are each and every one of us creative and innovative, but how do we form these teams, the right teams with the right people, and guide them to get that synergistic effect, to create high-performing teams? How can we use these teams to revolutionize the way we solve problems? So, I imagine a world where every child could learn by solving real-world problems that are of extreme interest to them at their own pace, using hands-on learning experiences. And we can use this open innovation approach and crowdsourcing to solve problems in unique ways. We should have been able to solve that problem of the foam impact while the crew was on orbit in minutes or days rather than months and years. And we should be able to do this, and we can do this. Not only that, but we can tap into this creativity-rich resource of minds around the world, young minds that haven't been jaded, if you will, in order to come up with innovative solutions to these problems. So, one of the first problems that I've been lucky to work on lots of different epic challenges in my 40 years of career. How do we solve this problem of, if we have damage to the wing leading edge on orbit, how do we send a crew out there to repair that damage and survive the searing heat of entry? Lots of companies were trying to solve this problem, and I watched them not so patiently fail and not come up with a solution. I said, you know what, I'm going to go in my friend Don Pettit's garage right here, the ultimate geek and fellow astronaut, and he has a laboratory garage, and I'm going to use the Friends of Charlie network, those experts with the know-who, the right people with the right knowledge. I'm going to team them up, and we're going to test lots of ideas in a psychologically safe environment where we could fail and learn fast and furiously. And we didn't ask permission. And we looked at dozens of different ideas, and we tested, and we failed. And me and Don had the time of our lives. And we were like two little kids, and this is when the light bulb went off in my mind. And I said, you know what? If we had teams of students around the world working on this epic challenge, I have no doubt in my mind that we would have come up with hundreds of new ideas that we didn't think of, and better ideas. But more importantly, how cool would it be for those kids to be a part in this and maybe see that their ideas can be realized? And not only that, but we could teach them what they need to know in order to realize what their imagination can only conceive. So, we were told, Don and I, that it's impossible to drill through carbon-carbon because it has silicon carbide, very tough, thin coating. Well, we designed, built, tested, fabricated, certified 2 drill bits that we were able to not only drill precise holes through the wing leading edge if we needed to repair it, but we could tap these precise holes, and we can fit them with screws and fasteners that we developed made out of the material that had eroded away or was damaged. But they told us it was impossible. The other thing we learned was that testing these round circular patches, these plugs, in an arc jet, you notice that the leading edge gets very hot because it's a protuberance to the flow. By connecting with a friend of Charlie, Pete Naffo, in one day he ran some computer cases, and he said, Charlie, you know what? If you make the thickness of that patch less than 1/10 of an inch, keep the bevel angle less than 6 degrees, they won't fail. And so what we did was we handed these ideas to Thiokol, who was working on these patches. They were able to develop patches that would not fail, and we only needed 18 patches to cover all the surface of the wing leading edge instead of 1,800, because what we had experimented in that garage was a thin patch, doubly curved. And we handed this technology off then to the engineers that did the due diligence in order to certify these patches for flight, and we flew them. And what happened was, what I realized was, a very small team working creatively can do amazing things. As a matter of fact, this team transitioned to a larger team at Langley, and we built and tested all different products, and we actually had a solution that we thought would have worked for a large pizza box size hole in the wing, if need be, which was amazing. Now, somebody said, Charlie Camarda, why don't you go out and see if you could teach this to young NASA engineers? And I said, okay, I'll do this because I think it's possible. You know, I think we could definitely teach this innovative conceptual engineering design process, but I want to pick another epic challenge that NASA can't solve. And one of them was landing of a space capsule. Okay, you know, in Apollo we tried to do it. We couldn't do it. All our capsules landed in the water. In Russia, they land on land. We have had a new program in 2005, the Constellation program. Unfortunately, that capsule had to land in the water also. So what I did was I took a bunch of young NASA engineers, about 30 of them from 7 different NASA centers, and some students. We went to Penn State. I took 4 professors, and we taught them. We immersed them in the problem, went through this methodology. We taught them how to ideate, think outside the box, using different techniques, lots of different techniques. Functional abstraction, functional decomposition, theory of inventive problem solving, biologically inspired design. And then we set them out there and we let them ideate, analyze, design, test, fail, and learn fast and furiously in the Learning Factory at Penn State. What happens was we had dozens of really cool ideas in that 1 week. These students worked intensely, couldn't get them to hardly go to sleep. They were working all hours of the night. And we selected only one of those ideas that was inspired by a biological system, a seed, and how a seed protects its embryo. Students came up, or engineers and then students came up with the idea of personal airbags. And what you see here is proof that this will work. We had one student, Sidney Doe, a master's degree student at MIT, working with 7 other students from Penn State and MIT, and those students only work part-time. And in 2 years' time, with very little money, with very little energy expended by the subject matter experts at NASA, I think it only required about 3 weeks of their effort, these students went through 3 different cycles and levels of concept development, looking at analyze, design, test, fail. And during that process, they went from analog airbags to single airbags to a full setup system and full-scale drop test. And here's where NASA contributed a crash test dummy. So very little effort. Okay, it's like a stone soup approach, linking the students with the next network of subject matter experts with the resources. And amazing, in only 2 years, these students not only developed a system that would work inside the constraints of the capsule that was already being designed by Lockheed Corporation, but they were actually able to save mass, a considerable amount of mass, to a vehicle that was struggling in mass, and they also save on-orbit habitable volume by about 26%. because this idea could be stowed so much easier. So my idea is, if we could do this with a small group of students, imagine on any one of these epic challenges, we have it worldwide, we have hundreds or even thousands of teams of students looking at multiple concepts simultaneously, maturing those ideas that industry, NASA, the government could cherry pick some of those ideas and advance the development of those ideas for the solution of these problems. Taking this one step further, we're going to scale it up. We're going to formalize it. We've been teaching this, and you're going to hear this from a colleague that's doing amazing work at Boeing. We have sponsors that select the Epic Challenge. The next one is an Asteroid Initiative, going out, grabbing an asteroid. We link them with multiple universities. We create the curriculum, okay, at the university level, high school, and even middle school level, and we reap the benefits of flow of creative ideas from below, and we have the mentorship from above, peer-to-peer and near peer-to-peer mentorship. So, imagine a world where students can learn working on problems that are of extreme interest to them at their own pace, student-centric learning based on how they think and learn. We could develop these epic challenges in every one of the industries and branches of industries, of the 8 industries that you saw here, where we would automatically generate a pipeline of students interested in that particular sector, in that particular industry. And what we're doing is we're linking this using concept maps so that now we can transition, we can bridge the gap from what the students know in high school to what they need to know in the university. And now I'd like to hand it back over to our great MC, and he's going to introduce you to Michael Ritchie to show you how this really comes together and works. Thank you very much.
Thank you, Charlie. So I first met Charlie through the advisory board for the Boeing Aerospace project, which you're going to hear about next, which is a capstone design project that we're really excited to be involved with. So Michael Ritchie is an associate technical fellow, currently assigned to support technology and innovation research at the Boeing company. Michael is responsible for leading a team conducting research projects to improve the learning experience for engineers and technicians. His research encompasses complex adaptive systems, learning curves, learning sciences, and engineering education research, focusing on understanding the interplay between knowledge spillovers, innovation, wealth creation, and economies of scale as they're manifested in questions of growth, evolvability, and scalability. His additional responsibilities include providing business leadership for engineering, technical, and professional education. This includes development of engineering programs in advanced aircraft construction, composite structures, and product lifecycle management. Michael is responsible for leading cross-organizational teams, as you hear about today, from academic, industry, and government, focusing on how engineering education must acknowledge and incorporate new information into the way that they train and educate. Michael holds a PhD in strategy, program, and project management with a focus on engineering research from the Schema Business School and is a Stanford certified project manager. Michael often represents Boeing internationally and domestically as a speaker and a presenter. He's authored multiple patents on CAD/CAM and has published a book on nanosciences and papers in leading journals. So please join me in welcoming Michael Ritchie.
Thank you. Good morning. I'm Mike. As Richie, as Bill just explained, I'm leading some education research at Boeing, and today I'd like to share a little bit about a research program that we have with multiple universities focused on distributed manufacturing and distributed learning. I think what you've heard earlier from Chuck and Bill and from Charlie about this new world, integrating digital concepts, integrating big data, looking at distributed systems and then harvesting intelligence from those systems is critical. And to move into that space, we need to develop the workforce for it. So at Boeing, we're focused on the top 20 critical skills, and one of the top ones is systems engineering and systems to systems thinking. And so we started thinking about how could we take our philanthropic dollars and how could we create a new environment that would enable kind of a microcosm of students and professors and industry SMEs to fuse together in a distributed, collaborative, project-based experience, and then put in the center of that experience an epic challenge. And last year we chose an epic challenge of feeding the world. We're looking at the projections of 9 billion by 2045, and we were looking at trying to increase yield using a UAV aerial vehicle, and I'm going to show you that in the last slide. And this year we've focused the students' RFP and their attention on first responders, meaning when you get to a site, if it's an earthquake or a fire or some natural disaster, how, as a first responder, can you deploy air vehicle resources and then gather intelligence? And I'll share that with you as well. So one of the reasons why we're really interested in this is we have roughly 12,000 courses in our portfolio. We teach to 180,000 people in 45 countries, and out of that portfolio, the engineering and technical programs, we invest somewhere in the neighborhood of 700 million hours. So there's a lot of training. So anything that we do as far as workforce development, its deployment across enterprises can have a multiplier effect. And then we have a philanthropic portfolio where we put money into the educational system as well. So we started looking at the threat of the workforce demographics to us, and this is very similar across the industry as far as workforce age distribution. And we started looking at this bimodal distribution you can see here in blue, and this wave of boomers and knowledge that's transitioning out. And we saw this as a threat not only to our sustain a business, but to grow the business as well. So we started looking at our portfolio of investments across education, both directed and non-directed, and where could we refocus this to make a better impact. And so number 4 is the one we're going to focus on today. Really looked at this notion of quality and knowledge transfer in the universities and pushing some of this knowledge, as far as knowledge workers, virtual, digital knowledge workers. How can we build an environment that would push that deeper into the educational paradigm? So you've seen this chart or something similar this morning about major shifts and forces that are shaping this. And globalization is one with the distributed shared risks and shared business model that's going on across the globe to get access to markets and things of that nature. Also the demographics. We're moving through the boomers, and the millennials are starting to move in and to develop that cross-cultural kind of environment. And then the social network, the digital natives, the kids that are actually embedded in this and play the mass multi-user games and then use social networkings and Instagram and Twitter and all of the stuff that they leverage to share information. How can we tap into that? And so the general consensus is that the traditional undergraduate programs, they're just not producing with the graduates with the skills that we need. And especially what you heard this morning from Chuck, as far as this integration of virtual and digital, and then the access to the data, and then acting on that data, it's going to require a different skill set. And so we're trying to figure out how we can partner with government and industry and then create a microcosm of that environment. And so on the blue, you can see this aerospace challenge that we put forth, and then some of the ways that we think that this project addresses those specific skills. And so, for example, the social networking. We have a social networking interface where the students interact, where we can collect unobtrusive data as they move through the design space. This is predicated right now on this Corporate U platform that we're using, and we have this. We have Siemens working with this mass multi-user kind of design space. So we're not alone in the way that we're thinking about this. The National Academy of Engineering posted some grand challenges. I think there's 14 of them. And this notion that the ability to find knowledge and the half-life of knowledge and the exponential growth of knowledge, getting access to it is critical. and that people, depending on where they're at in our business with the manufacturing, where they're at and the life cycle, they have very specific information that they need at the different intersections. And I have a chart I'm going to show you on that. And then, of course, everybody learns differently, and that this is going to require a different kind of team. And so we think that advanced manufacturing can play a critical role, and I'll show you how. There's a gentleman at MIT, Professor Sussman, who talks about complex socio-technical systems, and you've seen cyber and physical systems. His focus is on cyber, physical, and social. So complexity, as he would argue, interacts on the physical and cyber side, but that's complicated. But complexity ensues when you put people in the mix. And so we're kind of following some of his early work in this space. The AeroPace stands for Aerospace Partners for the Advancement of Collaborative Engineering. Our partners, of course, are Siemens, NASA, BYU. The NSF started an industry university collaborative research center there on e-design, so we're leveraging some of that work. We have Georgia Tech, based on their integrated digital manufacturing expertise, Purdue and Embry-Riddle, based on aero and mechanical engineering, and Tuskegee, based on their propulsion and mechanical engineering group. And so it really makes us think about this space as an integrated space, creating this microcosm on top of this digital and virtual world, and then putting the students in the center of that. And so it's predicated on four major ideas. One is this distributed stakeholdership, so that we can close that gap between knowing and doing that you hear often. And in that role, we have universities and industry. And we have an advisory board that drives that and governs that. Two, we're leveraging what we know about learning sciences. And in the past 20 years, if you know some of the publications that's come out of NAE and some of the investment out of DARPA and NSF on understanding how transfer occurs, especially on digital platforms, we're leveraging that information, trying to infuse that into our curricula and into our pedagogical approach. We're doing some really interesting research there, have multiple papers out there on the efficiencies that these new approaches bring as far as knowledge transfer and recall, pre and post, that kind of thing. We're also looking at, in the RFP that we put out to the students, pushing advanced manufacturing, additive, distributed, crowd, and cloud-based manufacturing. So we're really trying to think of how these boundaries, how to blur these boundaries and understand the interactivity and innovation that happens out of those boundaries. And the last one is this notion of leveraging the ubiquitous data in social networking, unobtrusive data where we can look at the students as they move through their design space. And so this is kind of a notional chart that looks at the topology. If you think about a network topology, at the top you can see a very high-level conceptual, preliminary, detailed design, test and evaluation, service after sales. It's really based on the NASA systems engineering model, a simplified version. And then on the left, you can see the traditional functional disciplines that we pull out of engineering. And the idea, as you move across this design space, is that you bring different levels of expertise to the problem space, and they have to converge at that level, and they have to optimize based on a time constraint, based on a schedule constraint, based on customer constraints. And what we're building in this topology, in this network, is a series of knowledge objects, and I can give you an example of one, if you can hit the slide there.
This is the layout of a typical maybe a three-bladed general aviation type of propeller.
So these are embedded lectures that have formative and summative assessments in them. And what we're finding is that this emergent learning that comes out of a strict discipline, say aero or structures, when they optimize in that space, what we're finding that the students are doing is they're moving to spaces that are outside their conceptual boundaries so that they can understand what the aero folks are imposing on them as far as constraints. They're understanding what the structures people are doing as far as sizing. And so you find this divergence where they're not in that functional track. They're not in the functional manufacturing engineering track or structures track. That they learn that learning is it's dependent and it's sensitive on where they're at in the product's life cycle and what they're trying to optimize at the space. And so these weak interrelationships, we're finding that the students are going through the primary learning, secondary learning, and tertiary learning just to understand how some of the other disciplines are arguing. So it's a very rich ecosystem where knowledge is transferred. And every click, every resource they look at, we can analyze. Where they were, what knowledge was created in that system, what knowledge they passed on from a network perspective. If you think of a network hub, we're finding out that some of them are generating a lot more connections as far as their knowledge, and we're actually getting down into the level where we can look at the knowledge that they're transmitting. So we can say in a Bloom's taxonomy style, if it's low, medium, or high synthesized information, and we can actually measure that information. And so what comes out of this, and we're not quite there yet, we've got a data analyst and a network specialist working with us. But what comes out of this is understanding the distributed cognition. And you heard that this morning about cognition moving through a product stage and then accessing that cognition based on its level of content, low, medium, or high. So we're trying to build this all out. If you've seen the MOOC hype about learning online, if you've ever taken a course out of Coursera, what this enables, and one of the things that we're doing with NASA, which really makes this special for the students, is we have experts across both fields that we're integrating to pull in to create these knowledge objects so that the students can explore these, and then when we're flipping the class, but it's like a reverse flip. They actually come to the lecture, they come to the lab, we define the problem space, they struggle with it, and then we send them here to get to their lectures. So it's kind of a flipping the environment. So what does that look like? And this is very early research, and we don't have all the pieces connected together, but I'm going to set this up before we hit the slide. So this is the student's desktop. On the right-hand screen, they have access to the three-dimensional PLM environment where they create the geometry. On the left-hand side, they have access to the social network where the patents, the papers, the MOOC-style lectures are all embedded. And we have both novice, where we have undergraduate, we have graduate level folks sitting shotgun. We have faculty on top of that and industry experts all residing, sitting inside of this digital space, watching the interaction of the students. So what I'm going to show you is, if you can hit that screen. So this is out of the BYU Design Center, and you have multiple students that are distributed. So these students are 2 from Purdue, 2 from Georgia Tech, 2 from BYU, and they're distributed, and they're working in this design space. So there's a rib team, and you see them working on the rib termination there. They break off, they get power packet strut in there, and they have to do their work. And so they're all interactively working in this space in an immersive kind of construct. And then on this structures, you'll see on the Corp U side, this is like a Yammer or a Facebook kind of interface where the students can go in, they can log, they can post things, they can move through resources. And in this case, you can see the structures team. And if you can select that, what we have is look at a time-stamped interaction of the students interacting throughout the course of the 2-semester project. So we have students that are moving through that space, and we can actually look at what students are where, what information they're using, what university they're coming from, what domain they're focused on. And so these interaction patterns and this analysis, deeper analysis of this data, and we have visualization people and some database people that are helping us to work and structure this for this next course that we're firing up, which starts in about 2 hours. We have to do a lecture for the students that are starting up here this afternoon. So the idea is to take all of this data across both platforms, the PLM platform and the social platform, and you can see some of these things that we think that we can derive out of that. We can look at these novice to expert kind of interrelationships. We can look at knowledge transfer to see if we can accelerate the acquisition of knowledge and the rate that it's acquired. And we can build into the environment's intelligence, prescriptive analytics, for instance, in structures. They're working, they're doing sizing, they need to run some CFD. The interaction from the unobtrusive data can allocate space for a server before they actually even need it. So you can right-size your IT requirements. On the clickstream part of this, the threaded discussions and the contents that's created and these real-time questions from faculty and industry, and a demonstration we did a couple of weeks ago, we brought in multiple engineers, high-level engineers, into the design space with the students as the students were going through their design iterations, and the experts actually guided the students on proper and improper design criteria. So, distributed cognition. So big data, one slide on that, and then I have a 3-minute movie that gets to the students' perception of this environment. So big data, if you think about big data, these clicks and picks, we actually set up pre-post test assessments in some of the lectures, which you can see here on the top. And you can see introduction to design. You can see pre-post, and if you look at pre-post, the measurements, they come in, and we started it at a nominal of 0 when you come in on the pre, and then by the time they move through the post, you can see on the introduction to the design space, they're at a 50%. They're learning 50% more of the objectives that we put in the pre-post based on the lecture lasting just 60 minutes. And so what we can do with that data as we disaggregate that data, we can look at the individual level and then collectively on the distributed level where these groups are interacting, trying to optimize some space. We can look at and then map that learning curve to the product's learning curve. And so if you think of trying to hit an efficient learning curve with manufacturing, that drives margins. And if you can look at the impact of knowledge and unobtrusive data as they move through a design space and you can change the slope of that curve, you can change your margins. And so it's a very early look at agent behavior and then agent-to-agent behavior in a distributed environment and how that behavior and that knowledge transfers as far as efficiency to the product service strategy. What you're seeing on the right-hand side is just each student's individual performance over the week and how they were engaged with the material and what student it was and at what times it was and at what platform it was on. We can push this out to social mobile platforms. We can put this on the workstation. And then one really interesting one is this First Responder Rfp. We went to LinkedIn and we posted requests on 5 or 6 of the first responder sites in American Red Cross and others, and we said we're thinking about this RFP for these students to design a first responder air vehicle that would get out there, deploy very quickly, gather intelligence, and then put that intelligence into a big data format that you could act on allocating resources to. And so this is what they came up with. You can't really see, but vehicle characteristics. It needs to deploy within 5 minutes. It needs to have a homing device. You should be able to center it. It should have infrared. So if you can think of first responders getting to the Haiti earthquake and opening up a box and deploying 5 different air vehicles that would fly off and look at the electrical power grid, the water system where people are cut off, where food needs to be deployed, that information could be gained very rapidly and pushed back into a dashboard so that resource allocations could be more efficiently monitored. And so this was the boots on the ground intel from the first responders, and we're having the students actually do that starting tomorrow. And one of the companies actually said, hey, if you pull us in, we'll buy whatever the students end up building. So there's a high level of commercial interest in this distributed, deployable, virtual kind of design criteria. And the last thing I have to show you before the quick video is in the RFP last year, we put a social problem in the center of this project-based distributed experience. And the social problem last year, as I mentioned, was you have to feed the world. And so you have a lot of folks saying, well, you're not trying to feed the world. Well, these kids really were trying to feed the world. And they were looking at a hand-launchable, simple UAV that would go out and look at topology, embedded sensors in the ground for nitrate distribution, water patterns, water distributions, map that to weather patterns, and then near-infrared to look at plant health, and then the near-infrared to also look at the topology to see what was tillable and untillable, if there were margins there that could be extrapolated, and then nitrate distribution and things of that nature. And the idea was, can we bump up the yield? And so in the RFP, we had one challenge that said, we want you to use additive manufacturing. And the 3 teams of 15 students each on this distributed platform used advanced manufacturing in one way or another. But one of the teams, cross-functional teams, actually printed what we think is the world's largest unmanned aerial vehicle that has camera and sensors and all of those things built into it. And it's right here. So they stalled a little bit in the manufacturing process because they spent more time there understanding the parameters of additive manufacturing and offsets and surfacing and things of that nature. But you can take a look at that later if you'd like. But it's just an idea where if you think of taking an ill-structured problem, putting it in a social context on top of a project-based experience, and then letting the students go with minimal guidance, with a few resources, this is the kind of workforce that Chuck was talking about that we need. And so at Boeing, some of our executives are saying, how can we scale this? How could we make 1,000 of these a year that we could pull into the company? Because these would be the folks that will change how we do business. And then last but not least,
it's rolling. Oh my gosh! Oh my god, that's awesome. I have been waiting to see that my whole life. It flies!
the experience was to take distributed team members across the geographical space and put them into constraints where they had customer constraints, quality constraints, schedule constraints, and cost constraints, and then move them through a design, build, fly project in 2 semesters. We work with NX Connect and Siemens and IUCRC. It's an industry university collaborative research center that was funded out of the National Science Foundation, and it's led by BYU. So this MMORPG CAD-CAM environment allowed students to immersively and at the same time share the same conceptual design space, even though they were distributed across geographically and distributed through their expertise.
With the ability to collaborate globally, we're finding that the talent search around the world is really turning into a global competition for talent. So more and more industries are recruiting people who have this practical work experience working on teams. So projects like this Boeing aerospace project really bring practical skills to the table.
So the additive manufacturing component was added in our request for a proposal when we first sent it out to the student teams. And we wanted certain components of the aircraft made using additive manufacturing processes. We didn't expect, but one of the student teams actually designed, we think, the world's largest additive manufacturing airplane.
Oh man, what just happened was magic. We got to see our plane fly 3 times, and it flew beautifully. And so that was the thing. This was a project that allowed me to apply those things I've learned to prove to myself and to Boeing that I'm an engineer. This proves to me that I can go out in the world, make a difference, change lives, and make great things that will help benefit the world.
I mean, when you think about it, students who don't know, have never designed an airplane, actually designed one, manufactured one, built one, and flew one in less than 2 semesters. That's an incredible achievement, and it's a testament to the students that are a part of this project.
It's gone well. I think the students have got a grand education out of it and a grand experience out of it. We've got to sit down and see how to improve it.
We're not just doing a one-off capstone. We're in it for the long run here, and we want to see a continual flow of kids coming out of these programs and into industry.
That a program like this really integrates so many things in terms of the technical, the people interaction. It's just the way we need to work as a company to be competitive in the future.
They have an untapped resource of creative students to get ideas from. And the students are doing the ground level work in maturing some of those ideas for Boeing to pick. It's a win-win situation.
Well, I think it's an unprecedented means and a rather affordable means of actually advocating to the young generation that our profession is still vibrant, it's still exciting. Boeing is a leading organization, that it's a place to go work for, and the fact that it's thinking of the next generation is a great advantage for them.
I think this program is so important to Boeing because it really is a microcosm of what Boeing is going through now. We're a global company. We have facilities and personnel all over the world that speak different languages, come from different cultures, all trying to provide value for our customers.
What we see in this is that there's an opportunity to have a different type of learning occur. One where students aren't told what they need to learn, but one where they discover the areas they're interested in. They can develop their own competencies as they go along. And if I was going to use technical language, I'd say they become intrinsically motivated. They want to learn. They're not being told to learn. And once you solve the problems of students wanting to learn, a whole new world opens up for you.
Thank you, and I just wanted to leave on this slide with the team and say probably one of the hardest parts of this was to get the professors and actually the professors actually gave up grading and allowed student peer review grading, which is like taking their sword away. So really working with innovative professors and open-minded people in industry and strong support from Siemens, we wouldn't have been able to pull this off. And being in the FOC club, we're planning on expanding this next year. So thank you for your time.